Okay, problem number 1. We have a 600 volt 3-phase Y-connected synchronous motor operating at a torque angle of 30 degrees, generating 400 volts, and a stator impedance, which we call Z armature, of 2 ohms at 90 degrees. Ignoring synchronous resistance again, so we're saying a 90-degree angle there. Determine E resultant and I armature. Okay, so a little bit of math that we're going to attempt here. I'm going to extend the page a little bit. We're going to start by putting in our reference line. So we're going to draw some and if I want to be really cool about this, I think, where's our tools? Right here. All right, let's bring this down. We said we want to be 30 degrees, right? So let's do that. Okay. All right, so we're 30. We have a 30-degree torque angle here. And this is what over here on the left? What voltage is that we have on the left there? E-gen. And we said that was 400 volts according to the information. We know we have okay, now we have to calculate at this point our phase voltage. So voltage phase, given the information, we have here, it says that we have a 600 volt line. Now given that we're Y connected, what does that mean our phase voltage is? 347, you bet. So we're going to take 600, we're going to divide that by √3, and we should get approximately 347 volts. That's what this is. So this is voltage phase, and that's 347 volts. Now, at this point, we want to determine E resultant. In other words, and I'll use a different color here, we want to figure out where this guy is. Now, I don't know that that's where it's at right this minute. All I know is that it's going to be somewhere in that area, and we can adjust it accordingly as we move here. So I'm going to just stick it there for now. We don't know what that value is, but we'll take a look at it and do a calculation and come back to that. Okay, so this was here. This was number 1. The second thing we have to determine is E resultant. Well, that's simply going to be equal to voltage phase plus E-gen. And again, we're using phasor addition. So we have 347 volts at an angle of 0 degrees. And we're going to add to that 400 volts. At what angle? 150. Good. 150. Oh, that's degrees. If we've done that correctly, we should come out to about 200 volts at an angle of 90 degrees. Okay, so we're going to go back up here and make a little adjustment here to this guy. So we weren't that far off. It's going to bring us down a little bit. And this is E resultant is equal to 200 volts at 90 degrees. Now, step 3, I'm going to insert a blank page here just because I can see my computer isn't keeping up. So, step 3 is we want to calculate our current in the armature. That's better. And to do that, we're simply, so that current that's flowing in the armature, which voltage is causing that? not phase voltage. That's power factor. What's causing the push? What's causing the electrical pressure to cause current to flow in the machine? E-gen. No, not E-gen, which only leaves one possibility. E-resultant. You guys are going to get it eventually, right? So we have to look at E-resultant. So remember, E-resultant is what causes the current to flow, but power factor is based on the phase voltage, not the E-resultant, okay? Try and commit that to memory, it'll help you out on testing. So we're going to take E-resultant and we're going to divide by the impedance in the armature. So in this case, our E-resultant was 200 volts at 90 degrees. Now I'm going to make sure you guys write in your angles, because when we get into a problem where your current isn't at 90 degrees, you're going to see how we have to deal with that. In this case, it worked out nice. We know, given the information, that we're 2 ohms at 90 degrees, and that will yield us 100 amps at 0 degrees. In other words, we look at this, they're at the same angle, and so they cancel each other out, leaving us with 0 degrees. So going back to our main here, we can put in our current. And this would be our current here. We said that was 100, whoops. Guess I need to change. This is 100 amps, angle 0 degrees. Now these are the type of questions you're going to get. It might give you a multiple choice question and say the current in this circuit is, and give you some options and you have to calculate it. All right, that's problem number 1. Any questions on this before we move on to problem number 2? Okay. Where's problem number 2? Is this it here? Yeah, there we are. Okay. A synchronous motor is connected to a load that causes the rotor to lag the stator by 25 degrees. The field excitation is adjusted to produce 420 volts. If the synchronous motor is Y connected, which they more than often are, to a supply of 480 volts 3-phase, and the stator impedance is 4 ohms at 90 degrees, determine voltage phase. All right. Well, we can do some of this right here, right now. So voltage phase, how do we calculate that? It's going to be 277. How'd you come up with that? You bet. We're going to take V line and we're going to divide that by the square root of 3, which in this case is going to yield us 200. I'm not going to go through the full calculation. It's third grade stuff. 277 volts approximately. Okay, the next thing, E resultant. That, of course, is going to be the vector sum of our E-gen and our phase voltage. Okay, so we know that when we look at, and I'll just go back here, let's cheat a little bit here and put some information in. So at this point, we know our E-gen is 420 volts, and we know we have a torque angle of 25 degrees, so that leaves us an angle of 155 degrees. Our phase voltage, we just said, this is V phase, and that is 277 volts at 0 degrees. Okay, so going back to our calculations, we're going to take those, put them together. So that equals 420 at 155 degrees plus 277 volts at an angle of 0 degrees. And if we've done that correctly, we should get 205 volts at what angle?
120.
How much? 120, correct. 120 degrees. Now, you see that doesn't work out to 90. Okay? So that is our E resultant right here. The next thing we have to figure out is our current in the armature. Now, once again, the current in the armature is being pushed by this guy right here, 205 volts. Now I'm going to go back here, and I want to put in our E resultant on this graph over here. Now our E resultant is not at 90 degrees. We have to make a bit of a change here. So we do this. It's over here somewhere. And I need to see, whoops. Okay, we're going to do this. You want me? Okay, fine. Have it your way. Move this over here. Make this a little easier here. Okay. Now we need to move this guy has to come at 90 degrees. Remember, we are at 90 degrees when we're doing this. Keeping our 90 degrees. Now we said that E resultant was 205 volts at an angle of 120 degrees. Where does that leave our current? 30 degrees, right? So, again, we could bring out my protractor here, bring her down here and see if we can't get this correct. I'm not quite at 120 there, am I? And so, let's do this. Okay, get rid of that. We're going to have to call it, it's a little bit too small to actually get that picky. So our current we know then is at 30 degrees. At this point, that's all we know. That angle is 30 degrees, or 30 degrees, right? Yeah. Okay, now we need to find our current. So going back to our calculation sheet here. So our current of the armature is going to be equal to 205 volts at 120 degrees, and we divide that by our Z impedance, which is 4 ohms, at an angle of 90 degrees. Now we take 205, divide that by 4, it gives us 51.25 amps. What's our angle? 30 degrees. Now we already knew that, but you simply take your 120, subtract 90, and that should give you your 30. Right?
Why is your impedance at 90? Sorry. Oh, it's
that's given information, and remember, we're neglecting resistance. We're saying it's so small that we're not going to worry about it, so we're going to call it 90, even though, like I said, we all know that technically speaking, it's probably closer to 18 or some angle like that, but for the most part, we're saying, let's forget about resistance for the time being, for simplicity's sake. We go back here, and that means we are at 51.25 amps at 30 degrees. Now, lastly, I think it asks for power factor, if I'm not mistaken. See what it says here. Yeah, so the power factor we have to come up with. How do we calculate our power factor? Say that again? Cos 30, you bet. Power factor is equal to cosine of the angle. And so if we take the cos of 30 degrees, we should equal 0.86 6, 6. All right. Any questions on that problem? Everybody's good? Makes sense so far? All right, good. Let's get down to our next one here. Okay, we're going to do some power factor correction. Now, I know this power factor correction using synchronous motors, this seems to get a lot of students in our TLM. And so we have a problem here. We're going to work through it and give you guys some tips on how you can make it a little simpler when you have to work backwards. Because what we're going to do on this problem, we're going to work forwards. We're starting with the basics. We're working up to an answer. A lot of the questions you're going to get asked in your TLM, they give you the answer kind of thing, and then they ask you, how did we get there? Okay, so there's some tips and tricks, if you will, that'll help you in that capacity. So we have a refinery station, pumps its main tanks using a 250 horsepower induction motor. It's operating at a power factor of 0.75. That's actually pretty good. And 85% efficient, along with a 55 kilowatt steamer. So there's a resistive load there. A 100 horsepower synchronous motor operating at a power factor of 0.8 lead and 91% efficient is to be added to move more raw materials. The refinery is fed by the secondary of a transformer of 600 volts. It says determine original plant power, the new plant power factor, and the new plant line current. All right. Very first thing we have to do here is this. Now, here's tip number 1. Regardless of the order in which you have to solve for the variables, if you can draw a couple of these triangles out before you can start putting any numbers in, you're going to be way further ahead. All right, now, there are certain triangles. So in other words, we're going to start with, I'm going to draw in what these actually are. So at this point, this one is our squirrel cage induction motor. Okay? The blue guy make that a little skinny. Okay, your blue guy, that includes the steamer. Okay, so this is the squirrel cage induction motor plus the steamer. And we have an orange guy. Gotta try and find orange on here. Make this look pretty. Let's make sure we're skinny. Yeah. So the orange guy is the plant. And we're going to call that new. That's after we've added the synchronous motor, which obviously is right there. There's our synchronous motor. Now, you guys have to be able to look at that and say, okay, where are our variables or our numbers going to go? So here we start with the really big of the squirrel cage induction motor. Then we add the steamer. So you could call this the blue guy. You could actually say that that's existing plant. That's another way of saying that. That's where we're at right now before we add the synchronous motor. Okay? You guys should be able to see that from here to here, we're going to have power of the squirrel cage induction motor, and then from here to here, we're going to have the steamer. Okay, so that's why we can call it existing plant or squirrel cage induction motor and steamer. Now, all we're doing when we go to the blue triangle is we're adding more P, more power. We're not actually adding anything reactive, so that's why the height of that triangle hasn't changed. Then when we add the synchronous motor on, clearly a synchronous motor has two circuit properties. We have resistance and we have some sort of reactive component. So when you take the red guy and add it horizontally and take the vertical component, which is opposite to our inductive component, you can see that we are left with this right here. So this here, that's our inductive. We'll call that, if you want, XL. Then we're going to add some XC, and that's supposed to be a C. And then we're left with X total. In this case, we should say Q in front of all of these because this is an actual power triangle. We're not looking at an impedance triangle. But that's the concept. So that's the tip. Before you even start adding in numbers here, be able to draw out the triangles like this so that when you get a question that gives you all of the information over here, but doesn't give you any of the information of the black triangle, you can actually work it backwards by looking at it visually. It's a major tip here. All right, now that everybody has those written down, I'm going to go into eraser mode here, guys, so that I can clean this up. So we're going to erase all this so we can keep this relatively clean. Okay, so you just have to remember which triangles are which. Okay, so let's start with some math. Whenever we are looking at power factor correction, are we interested in power output or power input? In other words, are we interested in what the load sees, or are we interested in what it draws from the circuit? What it draws from the circuit. That's what we pay for. We don't pay for whatever the output is to the load. Utility company could care less about that. It wants to know what you're drawing from their power line. And what you're drawing from their power line is power input, not power output. So the very first calculation, and I'm going to go and I'm going to put in we're going to insert a page here so we can do our math. Come on now. There we go. We're going to start with power out and calculate that accordingly. So at this point, our power output of the squirrel cage induction motor is going to be equal to 250 horsepower times what? 746. Good. And that will yield us 186.5 kilowatts. Now you guys are going to notice I'm dealing in kilowatts here because we're dealing with rather large numbers. We're dealing with over 1,000 watts or VA or VARs, and therefore we're going to deal with kilowatts here. In other words, there's going to be a little bit of rounding involved as we go through the problem. Now again, this is what the load sees. At the end of the day, the power company could care less what the load sees. It wants to know what it needs to charge you for what you're using. And that is power in. How do we calculate power input? Divided by efficiency. So we're going to take power out, and we're going to divide by percent efficiency. And in this case, that's going to be 186.5 kilowatts. And we're going to divide that by 0.85. So we have to leave it in decimal form, not a whole number, in order to come out with what we want for power input. And that gives us 219.41 kilowatts. Now, here's the next thing we're going to do. This is where you take your time. Let's go back to our triangles and put a number down. Okay, so we just found that the squirrel cage induction motor, so the power of the squirrel cage induction motor is 219.41. I'm not going to rate in kilowatts. I have limited room here, you guys, even on this big screen. So I'm going to count on you guys to understand that this is kilowatts. I'll maybe just stick kilowatts underneath. It doesn't look super neat, but then the numbers that we put on that horizontal, rather, you know that that's all power in kilowatts. Okay, next order of business. We'll go back to our math sheet here. We want to figure out power of the existing plant, or the power of both the steamer and the synchronous motor. So here's how we're going to do that. we're simply going to add the power of the squirrel cage induction motor. And again, we're dealing with input power plus the power of the steamer. Now I realize I'm probably going to take you guys into your lunch hour over here, but I'm going to want to get through this example today. Okay? So, in this case, we're going to take 219.41 kilowatts. And we're going to add, I think it's 55 as the given information, if I'm not mistaken, of the steamer. And that ends up being 274.41 kilowatts. Let's go back and write it in. So 274, oh, that's the total. What we could do, let me just erase this here. There's two things we can do. We can put 55 in here. Kilowatt steamer. Extend the page, and we could do something like this. Yielding us 274. 0.41. Okay. Now we know power of the plant. We can go back and deal with some squirrel cage induction motor variables. That's really going to be our next move here. In other words, we want to know what is S of the squirrel cage induction motor. How would we calculate that with the given information? You bet. We have a power factor of that squirrel cage, right? And I think it was 0.75. So we can simply take, back to our page here, so S of the squirrel cage induction motor is simply going to be equal to power of the squirrel cage induction motor divided by power factor. And so if we take 219.41, divide that by 0.75, that gives us 292. Let's see. Hard time. 292.546 kVA. While we're doing squirrel cage, the last variable to figure out there is Q of the squirrel cage induction motor. And we can use Pythagorean theorem for that, so we can simply take the square root of S squared plus, minus P squared. And again, this is all squirrel cage induction motor. So if we plunk those numbers in, we should come out to 193.5 kVARs. Now, this is an important number because this number is also going to be in the existing plant. So once again, we'll go back to our triangles that we made up. And so two values we can put in is 292.546 and Q, which we said was 193.5. Now, if we know that it's 193.5 for the squirrel cage induction motor, we also know that for the plant, that's the same value. So we can put that over here. Q plant is 193.5, and that's kVARs. We're going to need to know that here in a little bit. Okay. We're going to insert a different page, carry on with our calculations. So now let's look at some synchronous motor information. Again, we need to figure out power input, so we're simply going to take 100 horsepower, times that by 746, and then divide that by our percent efficiency, which is 0.91. And done correctly, we should come out to 81.978 kilowatts. Now, in the given information, what did it tell us about the synchronous motor as far as where we want to run it? We want to run it at what lead? 0.8, right? So, S sync is simply going to be equal to our power of our synchronous motor divided by our power factor. So we're going to take that 81.978 and we're going to divide that by 0.8. And that will give us our S sync, which is 102.472. And that's kVA. Now, given those two numbers, we can now calculate Q sync. We want to know all of these numbers because we're going to go put them on the triangles here shortly. So again, that's going to be just using Pythagorean theorem. There's multiple ways of doing it, but this seems to be the easiest. We're going to take S squared minus P squared. Again, this is all of the synchronous motor now. And if we've done that correctly, we should come out to 61.482. And that's kVARs. Let's go write it in. So it's going to be a little small, you guys, but hopefully we can get there. So we got Q 61.482. We had P, which was 81.978. And of course we had S, which was 102.472. Now, lastly, the orange triangle. So we put all this on our graph. We're on our triangles here. Now we want to figure out the orange triangle. So given all of that information, what do we end up with for S of the new plant, or the corrected plant, whatever you want to call it, and Q of the corrected plant? What do we end up with? Well, let's take a look at that. All we have to do is add up all of our power, including the synchronous motor, and then take our total reactive component that's lagging, which is the 193.5 kVARs, and subtract from that well, that's kind of cool, red, 61.482. We put those two together, they're opposite of each other, and that will give us our Q, and then we can also calculate our new S. So let's do that. Again, we'll go back to our calculation sheet and insert a new one. So Q corrected is equal to Q plant, so where we were at originally, minus Q of the synchronous motor. All right, our Q of our plant. We were at 193.5. We're going to subtract the 61.482, and we will end up with a reactive component of 132.017 kVARs. Power corrected. Now, because we had the synchronous motor, we know we had some resistance there. So we have to add P of the squirrel cage induction motor plus P of the steam plus P sync. If we add all three of those together, we should come out to 356.388 kilowatts. And then we can figure out S corrected quite easily by, again, using Pythagorean theorem. So we can take P squared plus Q squared, and this is all the corrected numbers. And doing that correctly, we should come out to 379.97 kVA. Let's go write it down. So our Q, let's do orange again. Good. Q we said was 132.01, I'm running out of room here, 017. And our S, we said was 379.97, it's a 9. And then, of course, our total P, we said was 356.388. Okay, that's 88. And again, running out of room here. Which brings us to two things that we have to figure out. Our plant power factor. We can do that here. Plant power factor, we're simply going to take P corrected over S corrected, and if we've done that correctly, we should have a new plant power factor of 0.938. And most importantly, this is cha-ching, cha-ching. What does the company get billed on? In other words, we need to know one final number, and the most important number probably of all the calculations is, what's my I line? What's my plan? What's Frito-Lay now drawing after we've made this correction? We're simply going to take S corrected, and we're going to divide that by E line times √3. We are dealing with three-phase, and if we've done that correctly, it should come out to 356.626, and that's amperes. I saw a lot of you shaking your head that you got the same numbers, so it looks like we've done that correctly. So again, one of the major tips here, you guys, and I know it seems like it's long and drawn out and all these darn triangles, but at the end of the day, in our TLM, when we ask you questions, again, we don't give you this pretty sequence where you can start with the squirrel cage induction motor and work your way to the right. We give you a lot of the values on that orange triangle, and then we say to you, go figure out the black triangle. If you can see it visually by just remembering how to write your triangles down, I think you're going to get a lot more right than you are wrong. And don't forget percent efficiency. Okay, that's it for today, guys. We'll see you in lab class.